Hey there, astronomy people. We are going to continue our stellar evolution diagram. I know you guys have all been waiting for this. So we're going to take out, there was two sets of notes that we did. We started with that stellar evolution kind of flow chart, almost like a concept map. And then we talked about a red giant. So they look like these two things right here. Okay. So we started with stellar evolution. We talked about how a star lives out its life till it becomes a red giant, right? Then last video, we talked about how a red giant forms, all right, with the contraction of the core, but the expansion of the surface layer. Okay, so we're going to go from what happens after a star leaves the red giant phase. Okay, so you can see here that we have our first fork in the road. Now, my fork is right at the bottom of the paper, and I ran out of fork and room. So what I'm going to have to do is use another fork and paper, okay? So what I'm going to do is I'm going to take this piece of paper, and I am going to continue this beautiful diagram on here. And then I'm going to get another piece of paper for this side, but you'll see as I start the flow here. So here's what happens. The red giant will fuse helium to carbon. All right. The sun will do this. It'll take about 2 billion years. All right. That's approximation of how long the sun will fuse helium in its core. So the sun will kind of have like a second life when it becomes a red giant. It's like a second go at things here. All right. But it will eventually run out of helium too. And this is why the fork in the road happens. The division at this particular place is whether we have enough mass in this star to fuse carbon into heavier elements or not. Is the star massive enough to take 6 protons, because that's what carbon has, to take 6 protons, this is 5, but let's pretend it's 6. 6 and 6, smash them together and get them to stick to form heavier elements, because that's what has to happen if you're going to fuse carbon. You have to have tremendous amounts of pressure and tremendous amounts of temperature so that the molecules, well, the atoms, are moving so fast that despite the fact 6 protons and 6 protons do not want to be anywhere near each other, they're going so fast and they're under so much pressure that they smack each other, hit each other, and they stick. Okay? So the sun will never have enough mass for that to happen. And the cutoff is the difference between what we call a low mass star and a high mass star. The sun is a low mass star. The cutoff is 8 solar masses. Now, this might come as a huge surprise to some of you, and I think this is the first time I've ever admitted this on film, but I'm a little bit lazy sometimes. And instead of writing out the words solar and masses, which takes like 3 seconds, nobody's got that kind of time. So what I do is I use the symbol for the sun, which is actually a circle with a dot in the middle. And then I write the letter M, like a subset there, the letter M. And that to me means solar masses. All right. One solar mass has the same amount of mass as our sun. One solar mass. It is the mass of the sun, in case you didn't pick up on the sarcasm. So what we're going to do here is we're going to say stars that have less than, that's the less than symbol, 8 solar masses. We'll go to the left side, what we call the low mass stars. Stars that are heavier than 8 solar masses. What separates them from the low mass stars is that these stars have the ability to fuse carbon. And we call these stars carbon detonation, right? Really what we call them is the high mass stars. These are greater than 8 solar masses. Stays heavy, okay? So that's the first fork in the road. So what I'm going to do now with this new sheet of paper is I'm going to put low mass right in the middle. And we're going to continue, right? Let's just put that right. Oh, look at that. Oh my gosh, like magic. And we're going to continue on as if I had plenty of room on this paper, right? We're going to just continue the concept map or the flow chart, whatever you want to call it. Okay. So here we go. Let's do that. What happens after the sun runs out of helium? We get the formation of what we call a planetary nebula. Planetary nebula. So what's happening is the star runs out of helium. And of course, helium is He. So it runs out of its fuel, and it no longer can fuse any form of elements into heavier elements. So fusion stops. And this is important, so I'm putting a couple asterisks next to it. Fusion stops. No more fusion, all right? So the star is pretty much dead, but it's not gone, all right? There's still some remains, and we can see them for a long period of time. So what is a planetary nebula? A planetary nebula is basically the outer shell of the red giant. So you guys might remember this PowerPoint presentation here. Loading. Okay. This is a picture from a telescope that probably not too different than the telescope I would have used at our star party if we had a star party, but we didn't because of the stupid quarantine. But anyways, this is what you would see if you look at it through a regular old telescope. This is called the Ring Nebula. And this was a red giant. And they always tend to form a ring or spherical looking shape because quite literally this outer layer right here of the Ring Nebula, the glowing part, that was the outer layer of the red giant. And in the middle, you see this tiny little white dot. That's the core of the red giant. And that's the next two phases, right? The next two phases of what the sun's going to do when it dies. Go to the next page here. This is a closer view. This is a much better, more powerful telescope now. And you can really see the ring structure. And then in the center, this white little core in the middle. Okay. So let me go back to my beautiful diagram. So planetary nebula, or what that actually is the outer layer of the red giant. And it just slowly expands away from the core, right? And as it expands, the nebula gets bigger, right? And it begins to expose the next thing. So it exposes the core. It exposes the core of what used to be in the red giant, right? That core is what we call a white dwarf, right? A white dwarf. These are insanely hot, super dense, very tiny cores of dead stars. The sun will ultimately become a white dwarf. Okay. We call them white because they're white hot. They're so hot that they're glowing in a whitish, sometimes even a bluish color because they're so hot. Why are they so hot when there's no fusion? These are the remains of the core of a star, right? That core has been fusing elements for billions of years. There is a lot of stored energy in there. And that's what's glowing, right? There's no fusion because that stopped a while ago. It's white hot because of stored energy. So some astronomers make the analogy, white dwarfs are kind of like retired stars, right? When people retire, They've worked their entire lives. They've saved up money their entire lives. And when they retire, they spend their savings. Well, that's what a white dwarf does. It's just spending its savings, right? It has all this heat that's just stuck inside there and it just slowly gives it off. Eventually, what happens is it actually runs out of that stored energy. So it begins to go from a white hot to a yellow to an orange to a red. And then it actually leaves the visible portion of the spectrum and moves into the next portion, the infrared, which our eyeballs can't see. When it does that, it enters into its last phase. Okay. We can't see this phase because it no longer gives off visible light. We can see it with infrared light that we can convert into visible light, but we can't see it with our naked eye. All right. We call this a black dwarf. A black dwarf, listen to this. This is fascinating. Is made of pure carbon. It is the size of the Earth, and it was made and forged in form in tremendous heat and pressure. What do you get when you take a lot of carbon and you apply a lot of heat and pressure for millions of years? You get a diamond. So black dwarfs are basically these big, giant, Earth-sized diamonds roaming around our galaxy. Folks, literally billions of them in our galaxy. If we could access one of those things, we'd have an unlimited supply of diamonds. Of course, if we drag the whole thing back to Earth, it would destroy our solar system and we'd all be dead. But we would have that really big diamond. Be pretty sweet for the last moments. But like, give it to your lady friend or your guy friend or whoever, and be like, hey, I got you this diamond, right? Destroy the solar system for you because I love you that much. Anyways, I digress. That is the future of the sun. It will be about the size of Earth. That's what a white dwarf is. It's the size of Earth in volume, but it has half the mass of the sun. So it is super, super dense. 1 tablespoon of a white dwarf is several tons of weight, right? You couldn't lift a tablespoon of white dwarf material. That's how dense it is. All right, folks. Death of low mass stars. Thanks for listening. It's been fun. And here we go.